I did pretty good yesterday. I got most of the guys' names. Looks like the sun didn't want to try to keep out, maybe. Yeah. Good morning, everybody. Welcome to another exciting morning of organic chemistry with me, Dr. White. Hi, important announcement as per my syllabus, because what we're doing today in lab and also on Thursday, I will enforce if you're late, you won't be in the lab. If you're more than 3 or 4 minutes late, I will not let you be in the lab or on Thursday. So hopefully if you have lab today, you have a long sleeve top on. You notice I got my acid shirts on, one of them, something old, and I won't say anything. All right, yesterday I was talking about reactions with alcohol. I gave you dehydration reaction, which you're actually going to do this week in lab. And I gave 2 examples, and I'll let you try it on your own before I do any more. It's a little complex, and I think it would help if you try it on your own before I do it again. There's some in the practice problems. All right, I was just about to talk about this new reaction, and this reaction is a simple one. Simple in the fact that it's not as complex as the one I just did with dehydration. If you take an alcohol and react it with a hydrohalogen acid, hydrogen halide, and remember X is the halogens, in this case chlorine, bromine, or iodine. What happens is HX, H+, and I showed you reacts with an alcohol to make water leaves, and the remaining Cl- or Br-, I- attacks what's called the carbonyl carbon and forms a bond. And essentially what you need to know is it replaces the hydroxyl group with the halogen from HX. Now, we're getting into this part of the semester, we're going to find out Dr. White is really biased when it comes to inorganic stuff. And all organic chemists are like this, most I know are. And this forms water, that's inorganic. And I put it on the screen, that's unusual. Usually I don't even put it on the slide. But I know some students say, what happened to the rest of it? Well, it's there for organic chemists. We don't balance equations unless we have to. And you don't even think about other products that are inorganic if we don't have to. We're lazy. And really the key thing here is what happens to the organic molecule when you make this organic. And that's this. If you want to put down the inorganic stuff, feel free to. It helps you. Last semester I had 2 students who were quite upset when I didn't. And I asked them to understand that I'm an organic chemist. And now we're getting into the easier part of the semester and the fact that when you look at an organic molecule, you'll find what's different. Look for what's not carbon, what's not hydrogen. That should get your attention like, ooh, oxygen. With the hydrogen and the carbon, alcohol. HCl, HX. What happened? Well, I replaced the hydroxyl group with the halogen. What's my R group? This. You break carbon-carbon single bonds? No. Well, I start with 3, I better end up with 3. The carbon with the hydroxyl group will be the carbon with the halogen. In this case, chlorine. I know there's 4 bonds to carbon. And there you go. That wasn't that hard. Why don't you try this one for your enjoyment on the somewhat overcast day. All right, looks like everybody's done. Before I do the answer, I want you to think about what did this have you do and what did you accomplish? Here, I put something, a complex organic molecule reacted with a reagent, taught you the general reaction, and said, apply it. You did. All right, let's take a look at this. What's different? I can't look anywhere else than oxygen. What's not carbon? What's not hydrogen? What am I reacting? This is an alcohol, carbon with a hydroxyl group. Alcohol, hydrogen, halogen. Remember, X equals chlorine, bromine, or in this case, iodine. What happens? You replace the hydroxyl group with the halogen. And in this case, what's the R group? Yeah, that whole ring in the methyl group. Do you break carbon-carbon single bonds? No. And now I have this. What happens? I replace the hydroxyl group with the halogen. On the carbon, the hydroxyl group was. It's on this carbon right here. It'll be replaced. What's the halogen? Iodine. And that's how you do it. By the way, I'm inoculating you against the chemistry instructor's favorite trick on the test, and that is put a big, scary R group. No, you're not scared by that because you know where to look. Now, the fun part of organic chemistry is not, well, if I mix this and this together, what did I get? You need to know how to do this. The fun part is, how do I make something? I'll do this one, and then I'll let you try one on your own. The question is, what's the question mark here? And we look at this molecule and say, what's different? What's not a carbon-carbon single bond, carbon hydrogen, ooh, a halogen. And it's on carbons. Have this. What am I reacting it with? I'm reacting something with HX. If I put it above the arrow, or if I put it like this, it means the same thing. Whatever's here reacts with this to make that. What's X? Halogens. If that helps any. And what's my R group? What's ever attached to the halogen? This is my R group. Going from here to there, have I added any carbons? No. Do I break carbon-carbon single bonds? No. So I'm going to have this ring. And my general reaction, which I didn't put up here, I will, is take an alcohol, react with HX, you make an alkyl halide, therefore the carbon with the halogen will be the carbon with the alcohol. Now, you've learned also that a double bond will do, you can sometimes, you may not get the right product depending on what I have, but for this part, one of the things I do, each test, I only limit the functional groups to what I've talked about for that test. On test number 2, I won't put any material from test number 1, unless I covered it also in the lectures for test number 2. Now, test number 2 will be like test number 1, other than historically, and I better write it this weekend, it's usually about 9 pages. It'll have, since I'm going to spend a lot more time on reactions, only about 35 points nomenclature names, about 60 points reactions, more time, more points, and about 10 points general knowledge. Anybody drive by a gas station think about they've got an alcohol, ethanol that's in the gasoline they're selling? Doesn't know. And on test number 2 and 3, historically, and I usually have 2 or 3 synthesis problems. still keep it to minimum. There's still cruel and unusual punishment, but more than. All right. If I take something, react it with HI, and I make this molecule, what would I start with? Have some fun. And remember always, I don't think I made a mistake, but it's your solemn responsibility, now being in my class, if I ever put a structure up there that doesn't have 4 bonds to carbon, just let me know. For those of you who weren't here, and didn't get your test that I handed back yesterday, see me right after the end of lecture day, and I have them with me. All right, looks like everybody's done. Let's take a look at this. Question is, what do you start with reacting with HI to make this molecule? And the first thing you should do is say, what's different? What's not carbon? What's not, ooh, halogen on a carbon. This is HI, which is really in HX, because X is an abbreviation we use, or not abbreviation, really a variable for any halogen. And this reaction, those are chlorine, bromine, or iodine. And what do we start with to do that? Alcohol. And what happens? You replace the hydroxyl group with the halogen. What's my R group? Whatever the halogen is attached to. R. Am I adding carbons here? No, so whatever I start with, I better end up with, I better start with. So I have 4 across. My 2 methyl groups. This is the carbon with the halogen. My general reaction says it's the carbon with the hydroxyl group. And that's how you do synthesis. That's the fun part of organic chemistry. The challenging part is, I need to make something, which is usually because you're in a company and it will make money for that company and help people out too. You'll need to know how to make things using synthesis. Later in the semester, I'll show you some of the ones I made and where I've worked, and they're also my patents. Example, like the fabric softener molecule, and a whole lot of other things you use in your daily life. Now, there's one problem with this reaction. This will never be on the test, so you don't have to write what I'm going to do down. Let's say I want to replace this hydroxyl group with a chlorine, but in the molecule I still want to keep the double bond. Question mark.
Where does CH3 go from the...
Did I miss one? Hold on.
Yeah.
Yep. It fell off. Thank you for pointing it out. Oh, there goes my perfect record today. Anyways, back here, question would be, if you have this molecule and you want to make a molecule that has a double bond in it, but this is a halogen, well, would this reaction do it? The answer is no. And here's why. I look here and say, oh, good news. I have an alcohol and HX, and I know that will replace the hydroxyl group with a halogen. But wait, I have a double bond. And this is the strength of functional group general reactions. React a double bond with HX. Break the pi bond. And it follows Markov-Nikols's rule. And if I were to run the reaction, I would probably get as the main product, depending about how much acid, but this is now going beyond the level of this course, but in general, I would get this, and I no longer have my double bond. I wanted to keep that. So, what do? I can't use this reaction. Well, this happens a lot in organic chemistry, and what generally happens after this type of problem, someone comes up with a different method to make a similar product that will overcome the problem. And that's the next reaction I'd like to talk about, and that's the reaction of alcohols with thionyl chloride. Again, on my test, I'll never have a name of anything. Thionyl chloride, SOCl2. It's nasty stuff. Today, you'll never handle it. But if I were to open a bottle of it here, it would react with the moisture to form hydrochloric acid. You'd see clouds. Well, I wouldn't do it here. I'd have to do it in the hood. Anyways, let's take a look at the reaction. The reaction is you take an alcohol, react it with thionyl chloride, and what you get, you replace the hydroxyl group with a chlorine. I don't think I've ever seen thionyl bromide. You could make it, but this is less expensive, so that's probably why I've never seen it. And everybody always uses thionyl chloride. And if you have to put a halogen, chlorines are quite good to put on things. And this is how you do it. Now, if you notice on the slide, you also get, this breaks down to sulfur dioxide and HCl, but on the test, you've already seen my questions are, give the organic product or products. So you don't have to know that. The nice thing about thionyl chloride is it only reacts with hydroxyl groups. This will not react with a double bond. One of the disadvantages of this course is I only have 16 or 18 weeks to teach you various general reactions. I don't have the time to show mechanisms why that's true. We'll just have to believe it. But anyways, this only reacts with hydroxyl groups and alcohols. So if I react this with thionyl chloride, I can either put it here or there. What happens? Alcohol, thionyl chloride. This is my R group. 4 carbons, it stays the same. Which carbon has the hydroxyl group will be the carbon that has the halogen. And now I know there are 4 bonds to carbon. And I've done this. And again, the beauty is if I use that molecule, I would keep the double bond. The only thing that would change would just be a chlorine. Why don't you try this one? What would be the product or products for the following? Organic product or product? Pin, 3 boys. Where have you seen that before?
question about the, what you're saying, plus thionyl chloride, that's the same thing as putting it on top of the arrow, right?
Yeah, this is something I'm going to be doing because all organic chemists are lazy. And I don't know if there's an IUPAC convention for how to write reactions, but this is one way I can write A plus B makes C. I can also write it this way. That means the same thing, A plus B makes C. There's another way I could, I usually don't, but it would be the same. Put it to me. And you see me do that with hydrogen and catalyst already. That's the same thing. How that evolved, I don't know. That's how I learned it. And one of the things I've learned in life, good habits I don't break. At least I try not to. All right, looks like everybody's done. Let's take a look at this. Again, the key is how do you know what to do? Look for something different. What's not carbon? What's not hydrogen? Hydroxyl group, oxygen and the hydrogen and the carbon, alcohol. What am I reacting it with? Thionyl chloride. What do you get? An alkyl chloride. Alkyl meaning R group, chlorine is called the chloride. And what's my R group? This. 4 carbons plus a methyl. So therefore, I better end up with 4 carbons of methyl. Which carbon has the hydroxyl group? That's the carbon that will have the halogen. And in this case, it's always going to be chlorine. And that's how you do it. I'll let you try this one on your own. What would I start with in a reactor with thionyl chloride to make that compound? Like I said, this thing will work with the chemistry. See, it puts a smile on my face. I don't know if I ever told you this, back when I started teaching this when we were in the old building, BIC, before they remodeled it, I had a classroom with chalkboards on the side, and I put up problems and make students go to the board to work on them. So I finally realized students would probably more likely like to pull their teeth out with pliers than go to the board. And I was wondering, why am I making these people miserable? So I stopped doing that. Oh, yeah. When you're done, look up and smile. Hi, looks like everybody's gone. Let's take a look at this. Oh, no, it's not a square, it's a ring. But this is carbon and hydrogen. What's different? Oh, a halogen on a carbon. And it's chlorine. What are we reacting something with? Thionyl chloride. What would I need functional group-wise? Alcohol. What's my R group? This. And therefore, since I'm not adding any carbons, whatever I end up with, I better start with. So I have my ring with 2 methyl groups. And the carbon with the halogen, chloride, will be the carbon with the alcohol. And there you go. And that's how you do synthesis, which is the fun part of organic. I say fun enough times you might not even believe me, but I believe it. All right. One of the things you should be doing in my class now and through the rest of the semester is asking the following question. Why am I learning this stuff? Well, the obvious answer is someone told you have to take this class. You want to get a good grade so you can get into a program or a school like nursing school. Well, why did they want you to learn it? Really? Why? Well, let's take a look at these last two reactions. Let's go out into the real world. How many of you are familiar with artificial sweeteners? It's a billion-dollar industry, maybe multi-billion in the United States, which means there's big money involved. And one of the more popular ones, I don't get any kickback from this company, somehow I gotta find out a way to do that, but is Splenda. And Splenda, I think you see in the little packets at restaurants, or you have it at home, you rip it, put it in your tea or coffee, it makes it sweeter. And the nice thing about these are 0 calories as opposed to sugar. Well, what is Splenda? Well, the main molecule that makes your tongue tell your brain, ooh, this is sweet. How that happens, I have no idea, but I do know the molecule is sucralose. Sucralose, and don't write this down, we'll learn later about this called the Hawthorne structure, but sucralose has, if you look here, hydroxyl groups. This ring I'll teach you about later on in the semester. Chlorine here on that carbon. Every end of the line, bend of the line is a carbon, and a chlorine there. And that's sucralose. Now, let's look at another molecule that I think you're all familiar with, and we'll learn later on during the semester. The structure, and again, don't write this down. This is called sucrose. This molecule has a lot of hydroxyl groups, which means it's got a lot of alcohols in it. Consuming this won't get you inebriated. It's not like ethanol. But you're all familiar with the product that this is, sucrose. It's otherwise known as table sugar. You know, the white stuff you put in your coffee, tea, or milk, or when you're cooking to make something sweeter. Has this structure. Yeah, that's organic chemistry too. We'll get into it later in the semester. And what happens is, the company that makes Splenda takes sucrose and reacts it with one of the two reactions I just showed you to replace some of the hydroxyl groups with chlorine. Which one? I don't know. It's a trade secret. I can guess. I've tried looking up their patents. No, I haven't in a while. Maybe it's online. But anyways, why are you learning this stuff? Because it makes things like sucralose, which is used in sweeteners. Now, a couple of things, this is my personal opinion. Remember, just because I have a PhD in organic chemistry doesn't make me an expert in everything. A lot of people don't realize this. Because you're an expert in one area doesn't mean you're an expert in every area, but I do know how to critically think, so I can use scientific thinking. And one of the things you don't know, but I'll tell you now, is smaller molecules, and this is on the borderline, is it small or not, that have halogens in it can be carcinogens. The very small ones are very, very bad carcinogens. That's known. Is this a carcinogen? There have been studies, and they say not really, but I wouldn't use this stuff. The other thing which came out a couple of years ago, and last summer I found out about it firsthand. Another reason, I used to use other artificial sweetener, but there was, I think about a year and a half ago in the New York Times, there was an article from these two medical doctors, how they tested on themselves and about 50 other subjects, that when you use either this or the other artificial sweeteners, that what it did is killed all the good probiotics in your stomach and gut, like that. And it took a while for your stomach to recover, which is not a good thing. How do I know about it this summer? Don't ask me how. I had a really bad case of food poisoning, and my doctor said, you know, you've got to bring back your colony, your probiotics, and you should take this and also eat yogurt. And I asked him, you know, I read this thing, and I like this doctor I go to because he's quite intelligent and well-read. He said, yeah, I heard about that. Guess what? I don't use those even before I saw that article, so I stopped, and it made a big difference in my life. So, will it work for everybody or not? Don't know, but the key thing is, why are you learning these reactions? Because these reactions are used to make things in your everyday life, like sweetener, artificial sweetener. And other places too, which you'll learn about. That's the nice thing about having a teacher who's worked in the real world. I know these things. All right. How are we doing time-wise? All right, I'm going to be turning the switch partially off. What does he mean by that? On my test, I'll never ask you the following, but I will use the terminology in lecture. The ACS final once in a while, remember what happens in 3301 states here. ACS once in a while asks a question about this stuff. And that's when we look at alcohols, there are three types of alcohols we can talk about. Now, I'm going to be using a convention I haven't used yet before, and that's where R group means anything with carbons. I can also have R, and this means R prime, one of them. That means that can be different from the R group, or it can be the same, just like X and Y in math. And guess what? You can have two primes. I've seen up to three I've used personally. When you go higher, you either use letters of the alphabet or numbers, and I won't do that in this class, but this is something I'll always use when I'm denoting. And what this means is the carbon with the hydroxy group has other carbons, one, and two hydrogens, so one type of alcohol. This has two R groups on the carbon with the hydroxy group, one hydrogen. These can be the same, like both could be methyls, or one could be methyl ethyl, or whatever. And here I have a carbon with the hydroxy group, no hydrogen, and it has three R groups on it, R prime, and R double prime. They can be the same or different. They could all be methyl. Each one could be different. This could have 5, this could have 7, this could have 10 carbons. And this is where R prime, R double prime, or this is like this, covers all that, just like in math, X, Y, and Z. All right, let's look at this one. When you have one R group on the carbon with the hydroxy group, we call that a primary alcohol. Again, I won't put this on the test, but I'll use the terminology in class. And it's abbreviated by one with what you call the degree symbol, and then the shorthand for an alcohol, ROH. When you have two R groups on the carbon with the hydroxyl group, we call that a secondary alcohol. And similarly, two with the degree sign ROH. And finally, when you have three R groups on the carbon with the hydroxyl group, we call this a tertiary alcohol. And it's abbreviated that way. Primary alcohol, secondary alcohol, tertiary alcohol. Now, some of the reactions I've just, like in the reactions I've just shown you, it doesn't matter if you have primary, secondary, tertiary alcohol. But now we're going to talk about some reactions where it does matter. So let's take a look at the next slide. And this is called oxidation of an alcohol. I haven't written this way. Let me show you another way I could write it. It's the same thing. This is maybe a little clearer for you. And if you take a primary alcohol and react it with an oxidizing agent. Now, on my test, I use the classic bracket O close bracket. That stands for one of the most classic oxidizing agents, oxygen. Oxygen here will do some very slow oxidations. Now, there are other oxidizing reagents you can use: potassium permanganate, KMnO4, sodium dichromate, potassium dichromate are standard ones. And there are a couple others too, but those are the ones. Later in the semester, right before the ACS, I'll remind you, because they usually use that. So if you see up at the top of an arrow a manganese, Mn, or chromium, Cr, that's always going to be this. And I'll remind you, if you look at the syllabus last week before the ACS, 3 of the days I'll be doing review and I'll go over some things like that to help you on the ACS. All right, so what this tells you is that you take a primary alcohol, you'll remove the hydrogen here, one of the hydrogens there, and form a carbon-oxygen double bond. We'll learn in a couple of chapters that's called an aldehyde. Another way to write an aldehyde would be this, but I like writing it this way because I think it's cooler. And I've done a lot of work with aldehydes, so they're quite cool. I like to draw the cool one. And let's look at this reaction. We're reacting something with a strange thing. What's that? Brackets with the no inside, oxidizing reagent. What do I have here? What's different? Alcohol. It's not only an alcohol, it's a primary alcohol, because there's one R group, in this case I'll call that R, on the carbon with the hydroxyl group. And what happens is, whatever the R group is stays the same, 3 carbons. Then the carbon with the alcohol attached to it becomes a carbon double bonded to oxygen. And you know there's one more hydrogen, so there's 4 bonds to carbon. And now I can throw in the rest of the hydrogen. And this is called an oxidation, and this makes an aldehyde. When we get into aldehydes, I'll teach you about where you find aldehydes and why it's good to make aldehydes. I will tell you this, both cinnamon and vanillin, which you know about, are both aldehydes. They're aromatic aldehydes, and they're important things if you like cinnamon and vanilla. And why don't you try this one? I should warn you, this is the part of the semester, through the rest of the semester. I'll always write the functional group on the right. Feel free to write it on the left, but again, good habits, I don't think. Is that large enough for you guys in the back? Yeah, need your binoculars. You see what so you can always ask me to draw on magic markers. Change the font and see. All right, looks like everybody, the last hydrogens are just going down, are gone. What do we have here? What's different? Ooh, carbon with the hydroxyl group, and we're oxidizing it, therefore it's good to know this is a primary alcohol. Here's my R group. It's attached to the carbon with 2 hydrogens hydroxyl group. I'm oxidizing it. And I lose the hydrogen here, hydrogen from the oxygen, form a carbon-oxygen double bond, and I form an aldehyde. What's my R group? These 4 carbons. Then I have this carbon right here, which is that carbon, double bond to oxygen, hydrogen. And there you go. 1, 2, 3, 4, 4 in the methyl. Yes,
So in order for it to be
what?
so in order for it to be a secondary, tertiary alcohol, the extra R group has
Right,
to be
we'll get
attached
to
the
that in a
carbon.
little while.
Okay.
All right, tertiary or secondary, you replace some of the hydrogens here with R groups.
Okay.
So a primary, the carbon with the hydrogens always has one R group. That's how it became primary, 1. The other way to look at it, which I don't, but maybe it helps you, is primary, the carbon with the hydroxy groups always has 2 hydrogens. Secondary, 1, tertiary, 0. But that doesn't help you correlate the primary, secondary, tertiary. Look at the R groups, and that's always will be the case. Oh, let's do another one of these. So why don't you try this one? What time flies when you're having fun with alcohol? 17, I said. All right, looks like everybody's done. Let's take a look at this reaction. Anybody know the significance of this molecule? It's ethanol. Where do you find ethanol besides gasoline? In hard spirits, like vodka and things like that, you know, good stuff. Beer and wine and champagne. And if I oxidize this with this reaction, what do I have? Primary alcohol, getting ahead of myself. Oxidize it, remove the 2 hydrogens and form a carbon oxygen double bond. We'll learn more about that. And what's my R group? Methyl. And that's the aldehyde you make. Now, a little while ago I said one of the questions you should always be asking yourself in this class is, why am I learning this stuff? Besides the obvious, you need a good grade in this class for some reason. The other thing is, why would somebody want you to learn this? Well, what you don't know is oxidizing agents, when they oxidize something, they are reduced. Hopefully you learned a little about that in general chemistry. One oxidizing reagent, sodium dichromate or potassium dichromate, I forget which, it's potassium, is orange. And when this is oxidized, this is reduced to a different chromium species of a different oxidation state, which is usually, and you'll do this in a couple weeks in the lab, not with this molecule, but other alcohols. It's usually a blue-green color or green color. So let's see, how can I use that? Well, how can you tell colors with a spectrophotometer? I think we've all used one of those, maybe in undergrad. In chemistry lab, it shows a certain setting that if it goes high, that means it's that color. Well, Why are you learning this reaction? Because the police use this. Police use this reaction. How many of you have ever seen, hopefully in the movies or on TV, the DUI test? That's the only place I've seen it, hopefully you too. And what do they have someone do? They blow into a device or blow into a balloon that they hook up to the device, do something, press a button, all of a sudden on the screen, either a meter or a digital readout, shows the percent alcohol in the person's blood. And somewhere, someone, medical doctor, came up with a correlation, how much alcohol you have in your blood, relationship to how much alcohol you have in your breath. And what they did is, they have a strip in there that has this oxidizing agent. You blow into it, there's alcohol in your breath, ethanol. It's oxidized, it changes the color, and the device has a chip in there that has a correlation to what color it sees to percent blood alcohol. So next time you see on TV, hopefully not in person, where they're showing the DUI test, that's organic chemistry, using a general reaction that you've learned. So now you can tell your friends, neighbors, loved ones, you can impress them about your knowledge of the DUI, hopefully not firsthand. I'm doing time-wise. Oh, I got And the question would be, what's the starting material? I'm going to let you try this on your own. Hint, big hint. Those who have lab today, please be on time. If you're more than a couple minutes late, you will not be allowed to work in the lab. And if you haven't picked up your test, see me right after class. I've got them. All right, looks like the last hydrogens just went down. What's different? Ooh, an oxygen. But it's double bond to carbon, which has a hydrogen, more carbons, which I'll call R. I'm oxidizing something to make that. And what do I oxidize? A primary alcohol. And what's my R group? 2 carbons. Then I have the carbon with the hydroxyl group. And I'm done. And that's how you do synthesis problems. Any of the general reactions I can put on a test, and I'm going to let you out a whole 35 seconds early. For those of you who don't have lab, I'll see you tomorrow. For those of you who do, I'll see you at 11 o'clock.